Algebra. Our today's speaker is Charles Young from the University of Hertfordshire, UK, and he will talk about higher current algebras and chiral algebras. Please.
Hi, thank you very much. May I check, am I audible?
Yeah, we hear you.
Great. So thank you. I'd like to thank the organizers for the opportunity to speak here today. I'd like to talk about some work which is in preparation with Zhengping of Tsinghua University and my student Laura Felder here at Hertfordshire. And the broad topic to start with is the notion of vertex algebras in chiral conformal field theory and attempts to pass to higher notions of vertex algebras, so vertex algebras in higher dimensions. By way of warm-up and background, then, vertex algebras are the mathematical notion which capture physicists' intuitions about operator product expansions in chiral conformal field theories in complex dimension 1. So the picture is that there's some object variously called a chiral correlator, or perhaps a conformal block or a co-invariant, which involves point-like insertions of operators into a complex curve. And one can consider the behavior of that object, that chiral correlator, as points become close to one another. So you have to picture, for example, this point becomes close to that point. And in such limits, the behavior is governed by the operator product expansion. So if you take, here is some chiral correlator, if you take the limit as Z1 goes to Z2, then the local behavior is captured in this structure, the vertex algebra state field map. And it obeys a collection of axioms, for example, Borcher's identity, which is the form of associativity here, which on the one hand are very natural from the point of view of chiral conformal field theory. They just drop out by considering the properties of complex functions in one complex dimension. But which, on the other hand, if you consider them in isolation, appear rather one of a kind. A vertex algebra is not really like any other algebraic structure. And there are deep relations to associative algebras, Lie algebras, and so on. But a vertex algebra itself is a rather one of a kind object. So what I want to talk about in this talk is attempts to generalize the notion of vertex algebras to higher complex dimensions. The background motivations here I'm not really going to go into, but they have to do with integrable quantum field theory and the methods of quantum integrable systems. And the main obstruction here is that the definition of the vertex algebras themselves appear to be so closely tied to the case of complex dimension 1. So there's a bunch of standard mathematical physics wisdom that says that Kac-Moody algebras are very special and tied to complex dimension 1. Conformal field theory itself in one complex dimension is very special because of the Virasoro algebra and so on. But what's nice is that in recent years, this intuition has started to break down substantially in potentially very fruitful ways. If you're prepared to work up to homotopy with higher and derived algebras. So I'll say later in the talk what I mean by that. And in the literature, there are broadly two approaches. They both center on factorization algebras in one form or another. One broad strand is more physicsy in nature and centers on holomorphic field theories or factorization algebras in the smooth setting due to Costello and Guillem. And there's a large literature here with very nice work. And the other strand is more algebraic in nature and centers on factorization algebras in their original algebraic setting due to Beilinson-Drinfeld. And it's that second strand that I want to talk about today. So factorization algebras are dual to objects called chiral algebras. And chiral algebras can be thought of, from one perspective, as a reformulation of what vertex algebras are, and a reformulation that's more amenable to generalization. So that's what I want to talk about now. So in terms of what you can hope to get out of this talk, if you know what a chiral algebra is, then this next bit is going to be pure review for you and nothing new at all. But if you don't know what a chiral algebra is, then I hope to give some hint in this talk. So the first thing I need is the concept of a D module. One has the sheaf of differential operators on, now in this talk, it's always going to be just affine space. So affine space of dimension k. And let's think that we're working over the complex numbers throughout. So one has the sheaf of differential operators, polynomial differential operators, whose global sections are just this algebra of x's and d's. And global sections will be enough for what I have to say today. And then D modules are modules over this algebra. And there's an important dichotomy between left D modules and right D modules. So what are left D modules? Well, the most natural example is just functions. So the structure sheaf O forms a left D module. Certainly differential operators naturally act from the left on functions. And then more generally, the sheaf of sections of any vector bundle is a left D module if, and then what extra structure do you need? Well, you need to be able to know how to differentiate sections. You need to say how the derivatives act on sections. So it better be a vector bundle with a connection. And the derivative operators commute. So it better be that the connection is flat. So any vector bundle equipped with a flat connection, the sheaf of its sections naturally forms a left D module. Right D modules, on the other hand, the important example for us will be the canonical sheaf. So the sheaf of top degree holomorphic differential forms. And I've written out here very explicitly how the derivatives act from the right. They act from the right by minus the derivative acting on the coefficient in any set of coordinates. So this is actually minus the Lie derivative in disguise. And the coordinate functions themselves just act by multiplication. So that's the most important example. But more generally, given any left D module at all, there's an operation called side changing, which exchanges it for a right D module just by tensoring with the canonical sheaf. So there's a rich theory of D modules, and what we need here is that there's a notion of pulling back and pushing forward D modules along maps of varieties or schemes. So please interrupt me, by the way, if there are questions, and I'm not sure if I can see hands, so please just shout out. So now, given the notion of D modules, the next important notion is that of chiral operations, which Beilinson-Drinfeld define. And the picture you should have in your head is a chiral operation is something that wants to take a collection of point-like insertions nearby and produce just one point-like insertion of something. So that's the rough intuition. And more precisely, we need, first of all, the diagonal embedding map that embeds one-dimensional space into k-dimensional space just along the main diagonal. That's a closed embedding. And we also need the open embedding of the configuration space of k points on the line into just k-dimensional space. Okay, so this configuration space is the space of pairwise distinct marked points on the affine line, A1. In other words, it's AK, but you have to subtract out all the diagonals, all the bits where any two of the points have coincided. So then in terms of those maps, suppose that you were given a collection of right D modules on one-dimensional space on the affine line. L1 up to LK, which you think of as these inputs over here, and M, which you think of as the output. Then a chiral operation is, by definition, just a map of right D modules on AK between these two D modules, and I have to tell you what these are. So on the one hand, you can take the exterior tensor product of these D modules L1 up to LK on the affine line to get some D module over A to the K. Then this is some pull-push. So what does it do? It pulls it back, first of all, to configuration space, and then it pushes it forward again. Now, the effect of that operation is just the following. It just means extend scalars like this. So here we just have global sections, a tensor product of global sections of these, the Li, I is 1 to K. But all we're doing here is we're allowing coefficient functions which can be potentially singular on the diagonal. Right? So that's what the input is. It's sections of, and then this exterior tensor product of these sheaves. So section like this, but allowed to be singular on diagonals. So it's really a section on the configuration space. It can become singular as the points collide. And then the output of a chiral operation has to be a D module. It has to be this D module. So the push forward of M, remember, is just another D module on one-dimensional space. You have to push it forward to k-dimensional space. I'm not going to go into the nitty-gritty of how the D module push forward works, but the upshot is the following. So you have something here on which you can act with a single coordinate z and a single derivative d, which is the derivative in the direction of the main diagonal A1. It's clear how general coordinates should act because they just pull back to that diagonal. What's not clear is how all the other derivatives should act. What should happen if you act with a derivative transverse to that main diagonal? And the answer is you just induce. So the D module push forward construction tells you to just induce as follows. So derivatives just pile up on the right like this, but with the proviso that the derivative along the main diagonal acts on the module as it should. So the D module push forward, you should think of as a section of this D module along that main diagonal, but thickened somehow to allow the other derivatives to act. So now, the point about chiral operations is that they make the category of right D modules in this one-dimensional affine space into a multi-category or pseudo-tensor category. What that means is they provide a notion of multi-hops and multi-maps. In other words, operations that take a collection of inputs, not just one input, and produce an output. And whenever you're in such a situation, you can ask for a Lie object in that multi-category, i.e. an algebra over the Lie operand. So let's just briefly, as an aside, recall what that means. So brief aside about operads. Operads formalize the notion of operations and composition of operations in algebra. So an operand is a collection of objects to be thought of as operations, and then a bunch of rules to be thought of as n-ary operations, where n can be some number of inputs, and then a collection of rules of how those operations compose to form new operations. So a classic example is the little squares operand, which is an operand in topological spaces, where the objects are nestings of squares inside larger squares, and the composition operation is just further nesting, as you see in the picture. So that's like the intuitive example of what an operand is like. Other examples are the binary trees operand, so the free operand on one binary operation. And so more generally, the operations in that operand are just complex linear combinations of binary trees, and the composition of such operations is grafting trees. And then the one that will be relevant for us, the Lie operand, still in vector spaces, is the quotient of that binary tree operand, that free operand, by additional relations imposing the relations you expect of a Lie algebra, namely skew symmetry of the bracket, what is secretly the binary bracket, and the Jacobi relation. So one can ask, as I say, for an algebra over that operand in this multi-category. And then you have a dictionary as follows. So the classic example of an algebra over the Lie operand is just Lie algebras. So if you take the category of complex vector spaces equipped with what are the multi-maps, they're just multilinear maps. So linear maps out of the tensor product. And you ask for a Lie object in that multi-category. What is it? It's nothing but a complex Lie algebra. So entirely analogously, if you now take this category of right D modules equipped with Beilinson-Drinfeld's notion of chiral operations, then by definition, a Lie object there is a chiral algebra on the affine line. So that is, what that cashes out to is a D module on A1 is a chiral algebra on A1 is a right D module together with a binary chiral operation, which is skew and which satisfies a notion of the Jacobi identity. For example, so examples of chiral algebras are immediately to hand. The first one, and in fact the one that I'm going to focus on in the entirety of the rest of this talk, is the unit chiral algebra. So the unit chiral algebra is just the canonical sheaf, which remember we noted before was a right D module, equipped with the chiral bracket given by the residue map. So in other words, what do sections of the canonical sheaf on the tensor product of two copies of the line look like? Well, it's dz1 times dz2 times some coefficient, which, as I stressed before, is allowed to be singular on the diagonal. And what you do, well, you just take the residue in the variable z1. So it's as nice as it could be. It's all set up. It wants to have its residue taken. You take the residue as z1 approaches z2. And the only subtlety is that you have to take the residue, the D module notion of residue, because, for example, so the residue of this simple pole over here is 1. So it should certainly be that this maps to just 1 times dz2. But then everything has to be compatible with the D module structure. So if you differentiate on this side by d1, it better be the same as differentiating on this side. So you can't just say that the residue of this thing is 0, as you normally would. You have to keep track of the fact that this is the derivative of that. So the residue here is dz2, and then tensor, this lambda 1 is to be thought of as a commuting variable that represents d1, the derivative, in this induced module that I described before. Okay, so that's the simplest example. And then more generally, and the reason why chiral algebras are relevant to discussing vertex algebras is that given any quasi-conformal vertex algebra, so any vertex algebra equipped with an action of the Virasoro algebra, you can think any vertex operator algebra. Frenkel and Benz-V tell you in their book how to build a vector bundle with a flat connection. I won't go into the details of that now, but let's just treat that as a black box. And then, so that's naturally a left-D module. It's a vector bundle with a flat connection. So by the side-changing operation I mentioned, you get a right-D module. And that right-D module is a chiral algebra, where the chiral operation is given as follows. And crucially, the point is that the state field map turns up here. So there's some generalization of the notion of taking the residue above. All that's changed is that we now insert here the usual state field map between. So what do sections look like? Well, instead of just being dz1, it's now a state in the vertex algebra times dz1. Are there any questions before I continue? So if not, I think the things to stress from this slide is just that there is this dictionary that goes from vertex algebras to chiral algebras. And in particular, the canonical sheaf is the very simple example that corresponds just to the trivial vertex algebra, one-dimensional with this OPE here. But it will turn out that even understanding this trivial case in higher dimensions is already the hard step. And at least the hope is that once you can do that, other cases will open up. Right, so one can ask, I guess the only thing that is not somehow morally clear from that definition is why it was the Lie operand specifically that one had to use. So why was it that these analogs of vertex algebras turned out to be algebras over specifically the Lie operand in this multi-category? And the following theorem of Beilinson-Drinfeld goes some way to explaining that. So recall that whenever you have a multi-category, you can look at the full subcategory on just one object. In other words, you can look at the multi-maps, the multi-homs from many copies of that object to itself. And in particular, we can do that with the canonical sheaf, omega. We can consider the operand of all chiral operations on the canonical sheaf. So the K-array operations of that operand are just these chiral operations. In other words, they're maps from the K-fold tensor product of the canonical sheaf, sections thereof, but allowed to be singular. So again, over the configuration space, to and then the push forward. And the theorem is that that operand is the Lie operand. So that's somehow morally where the Lie operand comes from. It's baked in, whether you like it or not. And now I can say what I want to do in the rest of the talk. So in the rest of the talk, I want to work over AN in place of A1. And as I say, I'll focus exclusively on the case of the canonical sheaf. And what I'm going to do is introduce a certain model I want to call the polysimplicial model. It's going to be a model of derived sections of the structure sheaf. As we'll see, we need derived sections rather than just sections. And completely analogously to before, we can consider the operand of all chiral operations on, and now that there needs to be a certain degree shift to put things into the correct degree, we will see. And it's now a DG operand. It's a differential graded operand. But otherwise, it's the same as before. So this, what we're supposed to do is draw the analogy between this line here and this line here. So this model of the derived sections is playing the role of functions on configuration space, functions which can be singular as points collide. And these are going to be the K-array operations of this higher vertex algebra. And the result is that, so you can ask, what is that DG operand? And the result is that it's quasi-isomorphic to the Lie infinity operand. So just a reminder about DG things and notions of homotopy, and in particular who this Lie infinity operand is. So first of all, about homotopies, the intuition that you should have is from the prototypical example of homotopies, namely homotopies between parameterized paths in topological spaces. Right? So a path can be homotopic to another path if you can smoothly deform one into the other. That's the intuition, but the relevant example for us is the notion of homotopies in DG vector spaces, i.e. cochain complexes over the field, where, recall what a homotopy is, it's some degree -1 map, and then two maps of cochain complexes are homotopic if their difference is of this form. It's essentially the anti-commutator of the derivatives with the homotopy. And then as soon as you work in DG vector spaces and allow homotopies, it's in some sense, it's no longer natural to consider Lie algebras, which are Lie algebras on the nose. Every time that something was true on the nose, it's most natural that it can now hold just up to homotopy. So an L-infinity algebra, recall, also known as a homotopy Lie algebra, is a generalization of the notion of Lie algebra, where the first generalization is that the usual Jacobi identity doesn't hold on the nose. Rather, the Jacobi eta is 0 up to a homotopy, and that homotopy is controlled by some threefold product, some ternary product, and so on all the way up. So formally speaking, an L-infinity algebra is an algebra it's an algebra in a multi-category, in a pseudo-tensor category, over the Lie infinity operad. And the Lie infinity operad is, what's good about it is it's free as a graded operad. So it's just the free operad on a collection of skew operations, one in each arity from 2 on up, sitting in certain degrees. And so it's free as a graded operad, and it becomes a DG operad when you endow it with this differential here. The details of this differential you don't really need to absorb, but the important example is what's sitting on the right-hand side here. In the case of just 3 inputs, what's sitting on the right-hand side will be the usual Jacobi relation. And then what this identity is telling you is that the Jacobi relation is D of something. So the Jacobi relation is not 0, but it's D of and then threefold product. Okay. Are there any questions before I continue? So if not, at this point, I want to change tack slightly and recall, in some sense, the origin of these DG algebras in this setting, why they naturally arise. And to do so, I want to talk about a class of objects called higher current algebras. And then I'm going to introduce the main tool, which is called the Thom Sullivan functor, that we use to construct models of derived sections. So let's go back to a very basic case and consider in some sense, typical vertex algebra, the vacuum Verma module, by which I mean the vacuum Verma module over some Kac-Moody algebra at level 0. So it's an induced module like this, induced from one vacuum state. And the crucial thing for the purposes of this talk is that when you induce from the vacuum state like this, what do all the other states look like? Well, they look like lowering modes acting on the vacuum. So a lowering mode is just the tensor product of an element of the Lie algebra G, and then some negative mode like this in the tail of the Laurent expansion. And geometrically, what's going on is you have to think that formal Taylor series are really functions on the formal disk. Or in fact, it's tautological. I mean, the formal disk is by definition the spectrum of the algebra of formal Taylor series. And then formal Laurent series, which contain these lowering modes, which you're using to induce from the vacuum, they turn out to be functions on the punctured disk. And this is somehow the magic fact. This didn't somehow need to be true. The punctured disk is by definition what you get. If you take that scheme, that affine scheme, and you remove its single closed point, the point of the origin, it's only got one, to get a new scheme. And what's special that happens in one complex dimension is that a new scheme turns out to be affine, turns out again to be spec of something, namely it's spec of the ring of Laurent polynomials, Laurent series. So geometrically, that's somehow why this construction works. If you puncture the disk, you get these new functions, which are singular just at that point, and that allows you to get this rich structure of this induced module. So here's some cartoon of a disk in higher dimensions. It's natural to try to run exactly the same program. Let's consider the disk in 2 dimensions. So the spectrum of the algebra of formal Taylor series now in 2 variables. You can play the same game. This is again some scheme with one closed point. You remove that closed point, but then something different happens. If you look at the global sections of the structure sheaf over the punctured disk, you don't get anything new. You just get the same ring of formal Taylor series that you had before. And this is a very familiar fact in the complex analytic setting, where it's known as Hartog's theorem in complex analysis. It's just the fact that, as we all learn, you can't have a complex analytic function in 2 or higher complex dimensions, which has an isolated singularity. They have to be singular along curves, some divisor. So this is an apparent obstruction to just naively trying to play the same game but in higher dimensions. But in higher dimensions, of course, the structure sheaf has higher cohomology. So one of the prototypical examples of sheaf cohomology is this one. Sitting in degree 0 are these functions as before, that we think of as raising operators. But sitting in cohomological degree 1, there's all of this stuff, which looks very temptingly like lowering operators, would-be lowering operators in dimension 2. So the idea of higher current algebras is to take this seriously. This idea is due, I think, to Veante, Hennion, Kapranov. And then there's also a very nice paper by William and Williams doing this in the smooth setting using the Dolbeau model. So what is the idea? Well, the idea is that in place of just global sections, so functions, you should consider derived sections. And recall that what are derived sections? So first and foremost, the derived sections are some cochain complex whose cohomology has to compute the sheaf cohomology, tautologically. But more crucially, more is true. So it's not just a cochain complex. Because we're looking at the sheaf, the structure sheaf, which is a sheaf in commutative algebras, what we should really be doing is taking the homotopy limit in DG commutative algebras to construct this derived sections, these derived sections. And that makes the derived sections into a DG commutative algebra, which is defined, it's not quite unique, it's defined up to zigzags of quasi-isomorphisms of DG commutative algebras. So that's what the derived sections are, and I'll give a very, very explicit example in a minute, if that's unfamiliar. And to do explicit computations, you need a good model. You need some convenient model of this homotopy limit. And there are various options out there. So the Dolbeau complex is one popular choice. The Dolbeau complex resolves the holomorphic structure sheaf. And then there are various others. The one I want to focus on today starts by picking a cover by opens. So recall that one thing you can do is to choose a cover of your scheme or variety or manifold by opens UI, and then consider the check nerve. So the check nerve is some semi-simplicial object in the category of whatever, varieties, schemes, whose co-limit is the manifold M you were first thinking of, or the variety M you were first thinking of. And then you apply the global sections functor of the structure sheaf to that semi-simplicial object, and you get a semi-co-simplicial object, because the functor is contravariant, so all the arrows flip. And it's a semi-co-simplicial object in commutative algebras, first and foremost, but you can think it's in DG commutative algebras. And then if your cover was sufficiently refined, such that all the opens and all their intersections are affine, in other words, if you have a Leray cover, then the cochain complex, the corresponding unnormalized cochain complex corresponding to this semi-co-simplicial object, computes the sheaf cohomology. But crucially in all of that, the trouble was that if you just go ahead and work with the usual unnormalized cochain complex, you lost the commutative algebra structure. You lost the associative commutative algebra structure. And that's bad. So that's why it's important to work in DG commutative algebras. And as I say, take the homotopy limit. The question is how to compute. So, so much for the general theory. Here's one more thing. So how to compute it? Well, there is this beautiful tool in rational homotopy theory called the Tom Sullivan or Tom Whitney functor. And what does it like to do? So it's a functor which likes to eat semi-co-simplicial objects in DG commutative algebras and give you back a DG commutative algebra. And it computes a model of the homotopy limit of any diagram presented as a semi-co-simplicial object. So the details of what it does on objects are written here, but I think it's better not to spend our time reading it. Rather, I just want to tell you what it does in simple examples because it has a very intuitive meaning. So here is a simple example. Let's consider the affine plane, so two-dimensional space. Two-dimensional space with a single point removed. And as we noted before, this is no longer affine, but you can cover it with the obvious chart consisting of the space with the y-axis removed and the space with the x-axis removed, like this. So our chart consists of two elements, this one and this one. And then the check nerve looks as follows. So it consists of those two opens and then their intersection. And what and then you apply global sections functor, and you get this semi-cosimplicial object here, which pictorially is just what I've drawn below. Okay, so pictorially, all it is the one simplex like this, with to one endpoint you associate functions on this chart, and to the other endpoint you associate functions on this chart, and then on the intersection, on the edge which joins these two zero simplexes, on the one simplex itself, you associate functions on the intersections of those charts. So functions which are allowed to be singular both on this axis and on that axis. And then what the Tom Sullivan functor tells you to do is the model that it constructs is of what form? Well, it consists of polynomial differential forms painted onto this simplicial set here. Okay, so that's what this V coordinate is. You think it's the coordinate on the simplicial set itself. So you take polynomial differential forms, that's this tensor factor, valued in, and they're valued in the algebra of sections where you've taken the intersection of all the opens, but crucially with certain boundary conditions. And the boundary conditions is what holds everything up and gives you the higher cohomology you need. So the boundary conditions are that when you pull back to this endpoint, the form should be valued, the coefficient should be valued in the algebra sections over this chart, and likewise for this end here. So it's not hard to convince yourself on staring at it that computes both. The cohomology is correct. So you see, let's consider, for example, degree 0. What is it to be in the degree 0 cohomology of this? Well, the differential is just the Durand differential on these polynomial differential forms. So to be closed is just to be a constant function, a constant zero form. And if you're constant, then what do the boundary conditions tell you? Well, the boundary conditions tell you that the constant must be valued in here, because it has to be valued on here, on pull back to this point. But on the other hand, it also has to be valued in here. So it has to be valued in the intersection of the two, and therefore correctly it has to be just a polynomial. It can't be singular in either of the variables. And you can do a similar calculation to work out that things are working in degree 1 as well. So what's nice is that you can continue to play the same game, but now with multiple points removed. And this is really a slide that I want to pause on, because there's somehow the essence of what is going on in these models is contained in this picture. So suppose we remove not one but 2 points from affine 2 space. And let's suppose that they're in generic position relative to my choice of coordinates for the moment. Then you play exactly the same game. You have to cover the space in a collection of charts, and it's always going to be this sort of rectilinear choice of charts where you've removed either the x or the y axis, the copy going through one or other of the points. So I hope it's clear from this picture here which are the 1, 2, 3, 4 charts of this cover. So what you did was for both of the 2 points, this point and that point, both of the marked points, you either removed the y-axis or you removed the x-axis. So those are the 1, 2, 3, 4 charts of the cover, and then their pairwise intersections. I've drawn all of them in the picture. But it's important to notice that not all pairwise intersections are on an equal footing. So the intersection of this chart here with this chart here is that chart there, where you still have this line has not been removed. But if you take the intersection of, for example, this chart here with that chart there, then you really have removed all the copies of the lines parallel to the x-axis and all the lines parallel to the y-axis. So that pairwise intersection is just the same as all the higher intersections as you go further into the bulk. And now, so you run this machinery of the Tom Sullivan functor, and you stare at it. And what does it tell you to do? It tells you to consider polynomial differential forms now on a tetrahedron. And those differential forms should be valued in the algebra corresponding to this picture here. So the algebra corresponding to this picture here is just this one over here. In other words, it's polynomials in x and y, but then you have to localize for all 4 of the lines that you removed. And then they have to obey boundary conditions. They have to obey boundary conditions in principle on every facet of lower dimension of this tetrahedron. So that's the model of the derived sections of the structure sheaf that the Tom Sullivan functor just emits, that it produces. But the observation is that you can do a little better than that, because not all of those boundary conditions are biting. So, for example, there is in principle, there's a boundary condition on this edge here, but as we just discussed, that boundary condition is actually empty because the intersection of this chart with that chart is you're already on this small open where all four lines have been removed. Okay, so, and this explains the orientation in which I've drawn this tetrahedron. When you stare at it, you realize that the only boundary conditions that are biting are the ones on the edges of this tetrahedron. If you flatten it down into the display, it looks like a square. So really, it's only those boundary conditions along those edges, those four edges around the edge of the picture, that matter. And what that means is that you can easily find a very explicit deformation retract from the differential forms on the tetrahedron down to the model of differential forms, polynomial differential forms on a square. And a square, of course, is just a product of edges. So it's an example of a polysimplex. It's an example of a product of simplices, in this case, a product of one simplices. So that's the crucial step. There is some deformation retract you can just explicitly write down that goes from the Tom Sullivan model to this much simpler model here, where you literally just have, in this case, polynomial differential forms on a square obeying certain boundary conditions. And it's that sort of model that I'm going to be using in what follows. So now, as we saw earlier, one of the inputs you need in this, in the notion of chiral algebras, due to Drinfeld and Beilinson-Drinfeld, is functions on configuration space. So similarly, just as in that example, I mean, it's not that example. This is not functions on configuration space. This is functions. This is the derived algebra functions on the space with two fixed points removed. But you can play a similar game on configuration space, namely, by which I now mean configuration space of points in affine n space. So you take affine n space, k times, so space of dimension n times k, and then you subtract out all the diagonals like this. And you run exactly the same program. So you construct a chart very similar in flavor to the one that we just saw to build this model, the Tom Sullivan model. And then you retract back to, and here is the definition of this polysimplicial model. So it's nothing but polynomial differential forms on some product of simplices of dimension n minus 1, which accords with the example that we were just looking at, was the two-dimensional example. So n minus 1 is 1, so one simplices, which is correct, because the cube is a product of one simplices. So in the general case, you need a product of n minus 1 simplices. And you need the k-choose twofold product. You need one copy for every pair of points that could be colliding. So you take such polynomial differential forms, and they have coefficients in this. This is a ring of functions where you've removed all the lines corresponding to every coordinate direction going through every point. So that's like the coefficients must be valued there in the bulk, as it were, of this polysimplex. And then as you approach boundaries, there are certain regularity conditions, certain very natural regularity conditions. So arguing in this way, using this deformation retract, you can show that this is a model of the derived space of sections. So the hope is so it is a model. And then the question is, what do you actually want in this game? So what counts as a good model depends on what you want to do. And let me immediately say a sense in which this would be a bad model. It depends on what application you have in mind. So if you're interested in cases where the GLN symmetry is important, where you really care about rotating the coordinates into one another a lot, then this would be a bad choice because it's somehow adapted to this very rigid rectilinear choice of charts that I was mentioning before. But if, on the other hand, you're in a situation where there really is a natural distinction between the different directions in this space, then this is a natural choice of model to be working with. So one obtains a model of the structure sheaf, and moreover, the sheaf of sections of any quasi-coherent, of any quasi-coherent sheaf of her modules. And now I can discuss some properties. So morally speaking, this DG algebra is supposed to be like the algebra functions on configuration space. It's supposed to be some derived version of that in higher dimensions. So a natural question to ask is, do you get analogs of the usual important relations in the algebra functions on configuration space? In particular, so a classic identity which pops up all the time are the usual Arnold relations, namely these identities here, where I'm writing a shorthand for Zi minus Zj. And the answer is yes, there are analogs of those. So to see that, one has to define this object, the propagator. So the propagator is to be thought of as the analog of just 1 over Zi minus Zj, the higher analog. And it sits in cohomological degree n-1 because it has this volume form sitting on the top. And it defines a non-trivial cohomology class by virtue of the fact that it's got all these factors in the denominator. And the presence of all these factors is what prevents it from becoming exact in this model. Like if any one of these was absent, then you could find a primitive for this. And it would be not only close, but exact. But the fact that they're all there means that you can't do that because any would-be primitive is not going to satisfy the boundary conditions. So that's what holds this thing up. It is what makes it define a non-trivial cohomology class. And then one can show by a lengthy but direct computation that the analog of the Arnold relations hold now in cohomology. So what does that mean? It means that if you consider this linear combination of propagators, it's not 0 on the nose. That would be too much to expect or hope for in this setting, but it is exact. It's D of something in this model. And there's a similar calculation, which I won't show here, but you just go ahead and compute the cohomology, and you find an explicit description of the cohomology as a graded algebra. So now the goal is to introduce the analog of the chiral bracket that we saw before. So recall that the unit chiral algebra, what made it into a chiral algebra was the fact that it was equipped with this residue map, also called the chiral bracket, which like to eat tensor products of sections, potentially singular on the diagonal, and give you back something in the D module push forward. We want to do something similar here. There's really only one thing you can write down, and that is, so it should be a map from sections over the tensor product of 2 copies, the product of 2 copies of n space, with coefficients in this model of derived sections. So again, morally, things which are allowed to be singular on diagonals. And then from there to the D module push forward. And I think I should mention at this point that you don't need to, you might ask, why is it not necessary to consider the derived version of this functor? Crucially, this is a closed embedding. And so the higher direct images vanish, and there's no need to consider the derived functor here. It's only on this side that you need to take this derived algebra functions. So as I say, there's really only one sensible notion of the chiral bracket you can write down, generalizing what went before. You take the residue in now all the different coordinate directions, and then integrate over this simplex. So in the case of 2 points, there's just one simplex to integrate over. And now this degree shift. So why is this degree shift necessary? If your goal is to get a Lie algebra or an infinity algebra, and if you want to do that, it had better be that the chiral bracket, the 2 bracket, is sitting in cohomological degree 0. So you just put it there by hand. You have to just shift the structure sheaf by some shift to put this into the correct degree, ensure that this sits in the correct degree. And then you find, first of all, that so the first test, if you like, is that the residue of the propagator is correctly 1. So if you put in the propagator times these, I should say that my lozenge here is just some notation for taking That's a product of the derivatives and then shifted like that. It's a product of the one forms and then shifted. So the residue of the propagator is correctly 1. So you have the expected pairing between the chiral bracket and the propagator. And now I'm not going to discuss in detail the proof of the main result, but let's recall what it said. So it said that if you take the DG operad, first of all, first part, definition proposition, first part, there is a DG operad whose k-array operations are the D-module maps like this. In other words, you can compose these in the right way to form the notion of a pseudotensor category, to get the structure of a pseudotensor category. And then the theorem is that DG operad is quasi-isomorphic to Lie, the Lie infinity operad. What does that say? So it asserts, more concretely, it asserts the existence of higher chiral operations. So in addition to this mu2, there's a mu3, there's a mu4, there's a mu5, and so on, all the way up. Not necessarily unique, obeying the L infinity coherence relations. And it's possible to give just a simple example of that. Here's the very simplest example. If we work in complex dimension 2, then the polysimplices are just hypercubes. So the model consists of certain polynomial differential forms on hypercubes with certain boundary conditions. And let's examine what happens to the Jacobiator. So the Jacobiator is some linear combination, this linear combination of operations of two-array operations composed to make three-array operations. So in total, this is some three-array operation. So that means it should be a map out of the three-array thing down to just one. And for 3 points, the dimension per hypercube is 3 choose 2, as I mentioned before. So you have one of these auxiliary variables, u, for every pair of points which could be colliding. 1, 2, 1, 3, and 2, 3. So this right-hand side here is recognizable as the Jacobiator we had before. So there are the 3 different pairwise collision geometries for 3 points. For example, maybe 2 goes to 1 and then 3 goes to 1, or maybe 3 goes to 1 first and then 2 goes to 1, or maybe 3 and 2 first get close together and then both of them go to 1. So what I'm glossing over here, what I haven't actually told you, is how the composition works. So there are some subtleties about that. I mean, I've defined the two-array operation here, but I haven't told you how it would act on some higher number of points. In other words, I haven't told you about partial application, which is part of the definition of an operand. You have to be able to partially apply operations. But that works, and this picture gives a hint of how it works. So it turns out that, for example, for this blue term here, you end up having to pull back first. So you have your starting point is some form on this 3 cube. You pull it back to this blue hypersurface, and then you do some integral on that hypersurface, and so on. Similarly for the 2 other terms in the Jacobi relation. And what this picture shows you is that there's absolutely no hope of the Jacobi relation holding on the nose in this setting, because you're literally integrating over different hypersurfaces for the 3 different terms, and there's just no way that these things will be agreeing in general. But as a sanity check, you can go ahead and try and write down the explicit solution for this first higher operation mu3 in this case. And the tools can only be really one thing. First is the Jacobi identity that the individual residue maps and the individual variables obey. And second is just Stokes' theorem for these simplicial regions. You've chopped up this cube into simplicial regions. And so it's a nice exercise. What you can do is you can write down explicitly by patching these regions together and considering the jump conditions. You find that mu3 is just explicitly given by a sum over 6 in total integrals over little simplices into which the cube is dissected. You get the right boundary or jump conditions in every face between them. So that this obeys the coherence relations. So that's the first example of how these higher operations look in this model for the unit chiral algebra. So now one can run certain applications of all this to try to make contact with other calculations in the literature. In particular, there's a nice calculation due to Gaiotto and collaborators, where they consider this diagram here, this product of propagators, triangle. And it's in a conceptually rather different setting. So in that paper, they really computing higher operation by summing Feynman diagrams. In this model, there is really now a model at the level of DG commutative algebras, and you can go ahead and compute what is mu3, higher product mu3 on this product of propagators. So this picture here corresponds to that element there. And it produces a result, which is a nice Turing check that this is getting some underlying model independent structure. And you can run similar calculation in higher dimensions. So I haven't discussed, but you can also compute the product in 3 dimensions and higher dimensions. Its form is more complicated, but calculation is just merely more involved. Nothing conceptually new happens. And you find generalizations for, in this case, the square diagram and so on. Okay, so I think at this point I will conclude. What happened? I talked about this model, the polysimplicial model of derived functions on configuration space of points in the model. It's possible to take down chiral operations, which fit with a pseudo structure, generalizing this structure that you need in the Beilinson-Drinfeld setup. The main result was that when you do that and consider just the shifted structure sheaf, omega, then that DG operand is up to quasi-isomorphism, which is the best you could hope for, is a copy of the Lie infinity operand. So that makes the structure sheaf into an example of a notion of a homotopy chiral algebra, in a sense that was recently, as in about 6 months ago, last fall, introduced in the literature in dimension 1 by Malikov-Schechtman. So it's natural to generalize their definition of a homotopy chiral algebra to the higher dimensional setting, and this is then a first example of such a beast. The general hope is that this particular model, the polysimplicial model, is well adapted to doing concrete calculations. And very roughly speaking, the idea is that it's quite finite, right? So it's well adapted to being put on a computer. In contrast to, for example, the Dolbeault model is a very popular choice. It resolves a holomorphic structure sheaf in terms of all smooth functions, but there are a lot of smooth functions. Right? So in some sense, this is, on the one hand, it's very elegant. It's very natural from the physics point of view because we're very used to working on superspace. But on the other hand, there's lots and lots and lots of smooth functions. So it's quite a large model, whereas this one is rather more sparse. Polynomial differential forms are very, very rigid objects. Of course, one should certainly ask about model dependence here. Like, I wrote down something in a particular model, and one can ask whether these structures are specific to that model, or if they are, as they should be, like, independent of that choice of model. And I don't really have a good answer about that yet. The situation is very subtle because of the need to work in D modules everywhere rather than just DG vector spaces, which means that you can't always, for example, do a deformation retract to the cohomology and then transfer structure by homotopy transfer to the cohomology, which you would like to do. But in D modules, the situation is more subtle. Nonetheless, the hope or the expectation is that the homotopy chiral algebras in this model, in this sense, can be turned into examples of higher dimensional chiral algebras in the sense of this seminal paper by Francis and Gaitsgory. And it's important to stress that it's been known since the work of Francis and Gaitsgory that chiral algebras themselves do generalize the higher dimensions. And this paper works in a completely model-independent setting, just working with the derived categories throughout. So there's certainly something to make contact with there. So the open problem is to check, as I say, the expectation that these homotopy chiral algebras match the higher dimensional chiral algebras in that abstract setting. And then, of course, finally, having got this unit chiral algebra, the hope is that it's relatively straightforward to introduce analogues of all the vertex algebras and chiral algebras that we know and love. So free boson, free fermion, the beta gamma system, BC ghost system, Kac-Moody algebras, and so on. So the hope is that the main obstruction is just getting very simplest example to work. Okay, so I'll stop there. Thank you very much.
Okay, so let's thank our speaker. So are there any questions, comments? All right, so if there are no questions, let's thank our speaker again. So we resume with the seminar next Monday. Goodbye, everyone.